Hello everyone and welcome back to another episode in Econometrics. We're going to start talking about a very important chapter today, which is latent factor models, and where the estimation method is recursive Kalman filter algorithms. The importance in this algorithm is that it contends directly with artificial neural networks in terms of face detection, even in moving objects, and hence Kalman filter algorithm kind of merges with nonlinear models, nonlinear estimation techniques or algorithms in order to develop more efficient and better artificial neural network algorithms or structures, basically in terms of programming. So we will start talking about latent factor models. There is a very good example in latent factor which explains why what is latent factor and how it is important. So suppose a rocket is leaving towards moon from the world, from Earth. Now inside the burning chamber of the rocket, about 1000 degrees of energy or if heat is produced, you see, to push the rocket up and then produce enough energy so that the rocketeer can steer the rocket around, However, it is important that inside the burning chamber of the rockets there is a constant amount of temperature between maybe 1000 to 2000 degrees is maintained, and it is very difficult to measure what is the temperature at any given time while such massive heat is produced, because any device that is put into this burning chamber that is going up to 2000 degrees maybe will probably melt. So the technique is to put a device outside the burning chamber, not inside. The outside the body temperature is measured with that machine or the device, and then has indirect estimation is of the outside chamber is taken. An indirect estimation is actually made taking the input from the outside chamber, where the output is basically giving you what is the probable temperature at the inside chamber at any given point. So that is latent factor. Actually, it is indirectly using a variable to measure the value of another variable, basically, and this process is called latent factor, something that is unobserved at any given time. For example, x is observed, but lambda on the other hand is unobserved at any given time, but the unobserved estimation is actually the actual one that we desired, right? So that is latent factor. The outside body temperature is not the direct measure of the inside body temperature, and that may sometimes vary in terms of estimation as well. But the outside body temperature, you have to remember, as it's not a constant value. Along with the inside body temperature, the outside body temperature changes, but at any given time, whatever the outside body temperature, it actually gives a probability approximation of the inside body temperature, and basing on that other estimations are made. So the input is basically an indirect observant, not a direct observant. So let's delve into latent factor models. Rewriting y equals beta xt plus ut is a regular equation, as we know. By relaxing x is observed, right? That is, we know. However, if we rewrite this equation as y equals lambda st in place of beta xt, we are measuring lambda st plus ut. St is unobserved or latent factor, because here st is not a direct measure of x, it's an indirect measure of x, and although there is a relationship between s and x that is expected, that expected relation varies with time. Extending to n dependent variables, y equals y1 to yn, and k latent factors, s is equal to s1, s2 to sn. Examples: term structure of interest rates, business cycle dating, identifying ex ante real interest rates that are not real, that are based on forecasts, real business cycles with technology shocks, KPM models of stochastic volatility. Now the beauty of this is that this is the reason why latent factors are highly used in making very accurate in-sample predictions. Benefits: a parsimonious parsimonious meaning restrained or careful, a parsimonious way of modeling dynamic multivariate systems. Dimensionality is a problem in even small systems of unrestricted vars. It avoids the need of using an ad hoc meaning as and when, formed for a special purpose. So it avoids the need of using an ad hoc proxy variable for unobserved variables. Example: KPM identification of ex ante real interest rate, etc., etc. The system of equation captures y equals lambda st plus ut. This model is called state space models, and the technique used for identification and extracting latent factor is called Kalman filters. Some important things to remember in Kalman filter is that the residual is normally distributed, so conditional mean or the conditional variance can summarize full distribution. Hence, these moments we needed for deriving the recursions, we need these moments for the derivation of recursion in Kalman filters. So we need to actually estimate conditional mean and conditional variance in order to in our recursion of Kalman filter algorithm. If the residual is not normally distributed, we use quasi-maximum likelihood estimators. Alternatively, GMM. In case of using GMM, we do not need this assumption at all, because GMM actually by default gives us means and variances. Okay. Now we have put a little light on quasi-maximum likelihood estimators while we were talking about linear equation autoregressive chapter, not the VAR, the regular linear autoregressive chapters, and there is a discussion specific chapter on quasi-maximum likelihood estimator. The beauty of quasi-maximum likelihood estimator, if you can recall, is that it is more important than OLS, it's more efficient than OLS, but it almost close to the efficiency of maximum likelihood estimators. So that's why it has some importance in econometrics. However, we will rarely see the use of quasi-maximum likelihoods in real-life applications. Probably GMM, on the other hand, is very, very important in economics and finance. Motivating example. Let's talk about two sets of examples. Empirical, using the filter to overcome the curse of dimensionality. Number one, term structure of interest rates. An example is US daily zero coupon bond yields. The time is in between 1988 to 2001, and we are talking about 6 variables. We have a 3-month, interest rate, 3-year interest rate, 7-year interest rate, 1-year interest rate, 5-year interest rate, and 10-year interest rate. Visual inspections show all these yields exhibit very similar dynamics, suggesting they are all driven by one or two unobservable factors. Interesting, right? So the dynamics that are all in this interest rate returns, all these returns which mature in different, highly different time periods, are quite the same, which means the latent factors or the unobservable factors might be quite similar. Now we will look into this, we'll surely estimate this later. In case of a single latent factor or k equals 1, the model of term structure of interest rate becomes interest rate in place of y put ri. Interest rate at time t is lambda I st plus uit, where I is equal to 1 to 6. St is a latent factor, and the residual is IID with zero mean and sigma square variance. Lambda I controls the strength of relationship between ith yield here. Lambda I controls the strength of relationship between the ith yield and latent factor st. So it controls the relationship, the strength of relationship between the interest rate and the latent factor. So lambda I here is called a factor loading. This equation is also called a measurement equation, where the residual uit allows for idiosyncratic movements in interest rate that are not explained by movements in the factor. Hence the parameter sigma I controls these idiosyncratic movements, strength between the residual and the interest rate. Now, in a matrix form, we can simply write this equation as RT equals lambda, capital lambda ST plus UT, which is a measurement equation, and the capital lambda encapsulates lambda I to lambda 1, lambda 2, lambda 3 up until lambda 6. To complete specification of interest rate equal to lambda I plus uit, now we are remained with specifying latent factor st only, as uit is independent dynamics of interest rate must be captured in dynamics of st. So as the residual is independent, the dynamics of the interest rate must be captured in the dynamics of the latent factor. And as I said, lambda is called factor loading as well. This equation is measurement equation. The simplest representation is to allow st to follow autoregressive one, because it captures the dynamics of interest rate. So to allow autoregressive one model, allowing st to have autoregressive one specification, the equation is st equals phi st minus 1 plus vt, now where vt is IID with zero mean and sigma square variance. Now vt is the disturbance terms of, and at the autoregressive parameter now AR captures the dynamics in this equation, and this equation specifically devoted for st is known as the state equation. So when you combine both of the equation, measurement and state equation, you have the state space model. So let's start with discussing an example. Business cycle dating. Commonly GDP growth rate changes y1t, changes in unemployment y2t, movements in unemployment y3t, and retail sales y4t are observed variables in business cycle dating problem. These are the factors that are indirectly or directly affecting peaks and drops in a business cycle. The business cycle is, on the other hand, unobserved. where these variables are observed variables. So the model is looking into the measurement equation we have yit lambda ist plus ut. ST is latent business cycle, and you have the residual UIT, and that is a disturbance term. To capture potential cycles in the latent factor, the dynamics of ST represented by the measurement the state equation, right, which is S is equal to P phi 1 st minus 1 plus phi 2 st minus 2 plus Vt, which is an AR2 model. Vt is disturbance term with zero mean and sigma square variance. The assumption that UIT, the residuals, are independent can be relaxed now. Okay, it's not independent. It's not. We can think that the residual UIT is not IID anymore. Rather, the disturbance Vt is IID. To include additional dynamics with this ST by specifying, so now we can relaxing the independence of residual, we can include additional dynamics. Okay, we can further include additional dynamics in the latent factor by specifying UIT equals delta I UIT minus 1 plus omega IT, right? So lag of the residual is determined by delta plus now the residuals disturbance is omega IT. So you specify it in this term. Where this time, as the residual is not IID anymore, omega IT is on the other hand IID with zero mean and sigma square V variance. Beautiful, right? So we can relax our residual in, taking considering it as dependent on his lag, and another equation can be presented that kind of resembles the equation as state equation and autoregressive one equation, AR1 equation. Theoretical KPM. Let's talk about KPM now. Another model. We are just talking about how we can specify different models in terms of latent factor models. So KPM, where YIT observed excess return on asset equals alpha I constant plus beta I MT. MIT is observed excess return on portfolio. Beta I is beta of the ith asset. So observed excess return on asset, observed excess return on portfolio. UIT is IID with zero mean and sigma square variance. KPM should be specified in terms of excess returns in all invested wealth. KPM is unobservable. Hence, MT is serving, MT which is the portfolio's return, is serving as a proxy. So you have assets return, you have portfolio's return. Alternatively, instead of using MT as a proxy, we can simply use a latent factor ST to treat the excess return on the wealth. And so KPM becomes UIT equals alpha I plus beta I ST instead of MT plus UIT. Dynamics of ST helps to identify dynamics of aggregate wealth, and the dynamics of ST, this is the measurement equation. Dynamics of ST by default is represented by state equation, as we know. Ex ante real interest rate. What does it mean by ex ante? Ex ante is forecasted real interest rates that are not realized at a given time. Decisions are made on ex ante real interest rate basing on unobservable factors, such as they are based on expected inflation rate, which is not a real one but expected inflation rate. The relationship between ex post and ex ante real interest rate is ex post real interest rate is inflation interest rate minus the inflation rate is the nominal interest rate. IT is the nominal interest rate and PIT is observed inflation rate. So when you are using expected inflation rate, well, the difference of expected inflation rate or observed variable, that is ex post. But when you are taking the inflation rate that is not observed. I'm sorry, you're taking expected interest rate that are not observed yet, that are assumed, that is ex ante. When you're taking inflation rate that are observed and realized now, is no more assumption, that is exposed. So the rewriting the interest rate, we have RT equals alpha plus alpha plus I minus the interest rate is I minus RT, the ex ante minus alpha plus RT. So we are doing what? We are taking I minus RT plus minus alpha plus RTE plus minus RT. So what are we doing here actually? We are taking the difference between ex ante and exposed interest rates. That's all, nothing else. Just the ex ante and the exposed interest rates difference is taken here. I minus RT so delta R, basically delta R is taken, and when we do that, we so we are left with y equals alpha plus st plus ut, that is the regular equation. So y equals RT in place of y equals RT, st plus alpha equals I minus RT, the ex ante real interest rate. So what do we have? We are not thinking in terms of lambda. We are not putting the lambda, bringing the lambda here. What we have is that first ex ante minus exposed. So the changes, signs inside change, that's all. Ex ante minus exposed, that's all, and then we cut them off, and then we are mentioning the measurement equation, and we are saying how this measurement equation merges with the interest rates difference, ex ante minus exposed, the realized actual interest rate. So you had ex ante interest rate, you have exposed interest rate, and that gives you the deviation from your forecast to the real observed interest rate. So when you didn't know about inflation rate, when you do know about inflation rate, gives you some kind of degree of deviation which we want to reduce in different iteration. So st plus alpha gives you I minus RT ex ante real interest rate. Residual, on the other hand, is the error in your expectation or in your assumption, because you're simply taking a difference between ex ante minus exposed. So that is the error in your expectation. It is quite simple specification with an error term now in place. So let's looking into this now. The most important thing is that to start talking about recursions in the Kalman filter, or to see how the algorithm in Kalman filter estimation is being produced. Kalman filter is an algorithm to form predictions of k latent factors based on their conditional mean, and thus update these predictions in a systematic fashion. So based on the conditional mean, first predictions are made, and then these predictions are systematically updated, quite similar to neural networks. Feed forward algorithm in neural networks, when as soon as new information is fed into the system, the predictions are updated in a systematic way as more measurements of the n observed variables become available. Here now we present both univariate and multivariate algorithms, n equals k equals 1 and multivariate is both in terms of n and k, they are greater than 1, highlights the recursive structure and other properties of the algorithm. In deriving the algorithm, we assume parameters of the model are known. Generally what happens, we take initial parameters in the model with predictions going forward. Generally the earlier initialized parameters are either removed, or it is best to start your process using parameters that are estimated with maximum likelihood estimation if you don't know the parameters. So it is best to start by estimating the model parameters with MLE and then moving forward from there. Univariate. Consider the univariate model n equals 1 observed dependent variable y and k equals 1 single latent factor s. So y equals lambda st plus ut is the single latent state equation, and s is equal to phi st minus 1 plus vt is the measurement equation. Here the expected value of the residuals are not UTVT means we are expecting the residual and the disturbance are not correlated. There is no relationship between these two variables, or there is no covariance, and hence the parameters lambda, phi, sigma square, the variance of the residual and the variance of the disturbance term are not are known parameters, right? Basically, if they are not known, run a maximum likelihood estimation to estimate them. Prediction. Consider forming a prediction of ST using information at time t minus 1, that is defined as ST conditional upon prediction of ST conditional upon information at t minus 1 equals ST in the expected ST in the last period, t minus 1 ST. Taking conditional expectations now, so ST conditional upon information at time t minus 1 is equal to ST of last period equals now ST, the dynamics of ST or the state equation says phi ST minus 1 plus VT. So phi ET minus 1 ST minus 1, that was the initial latent factor ST, which is phi ST minus 1, that updated slightly. Phi ST minus 1 is conditional upon t minus 1, which becomes, so if we're talking about S10, we are the left hand side, that is phi naught, that becomes phi S naught conditional upon time, information at 0, phi S naught 0. Now last period's expectation on the disturbance term by normality assumption or by definition is ST minus 1 conditional upon t minus 1 equals last period's ST minus 1. So S naught given on information at last period equals S naught. So S1 is phi S naught, while S naught is simply S naught, as we know. Variance of ST given information at time t minus 1 by definition is presented with capital P, PT, which is given information at time t minus 1 or conditional on time t minus 1 is taking the last period's expectation, which is simply the difference between current ST minus, so basically it is simply the difference between S1 minus S naught. ST t minus 1, as we know well, is S10, right? S1 at time t minus 1. So ST minus ST conditional t minus 1. So S1 minus S1 naught and squared, that is the variance. It is one step ahead. This variance is also known as one step ahead prediction error. Latent factor estimation of S currently and latent factor of estimation of S in the last period. Conditional at time t, latent factor S conditional at time at information available at time t minus 1. So this gives you one step ahead prediction error by definition. And what will happen? What is the difference? Well, st is 1, s1 0 basically is phi s0 0, right? So s1 minus phi s0 0. So we need to remember these as we go forward. S0, then S1, S0 is S0, S1 0, S0 conditional on 0, or is phi S0 conditional on 0. So now subtracting st minus 1 from the state equation, we have st. First we had st equals phi st minus 1 plus vt, and we subtract st minus 1, which is s1 0, right? In both sides we have st minus 1, or simply remember in the sense that s1 0, you have phi s0 0, right? So replacing them, now you have phi st minus 1, so phi s0 minus s0 0, so s1 equals phi s0 vt, so phi s0 minus s0 0 plus the residual. It is easier to remember in this manner with 1 and zeros, right? So this is the state equation, and we are just with s1 we are just subtracting s1 conditional at 0. And what is this difference? This is giving you one step ahead prediction error, because this difference if squared gives you what? Gives you the variance, gives you when this equation squared gives you, let me just go up, yeah, by definition gives you the variance. This equation gives you the variance, squared gives you the variance of the latent factor model, right? And so we have, this is represented with phi s0 minus s0 0, so s1 equals phi s0 0, phi s0 minus s0 0 plus the disturbance term. So we can write it as s1 minus s1 conditional 0 equals to phi s0 minus s0 0 plus disturbance term. And so we square it, the conditional variance. Now we are measuring the conditional variance p1 0, which is, we square it and we put these value inside in the squared, and we do a plus b whole square, and we break it down to this equation, and then ultimately we are with this equation. Now what do we have here is that phi square at minus 1 st minus 1, so s0 minus s0 naught square plus v square plus 2 phi e s0 minus s0 0 vt. And we just talked about conditional variance before. P1 0, which was the difference between s1 0 minus s0 0 squared. Now we are talking about P0 0, not P1. P0 0 is s0 minus s0 0 squared. So what's the difference? One more time. P1 0 was s1 minus s1 0, or not, time is 0, right? S1 minus S1 naught. On the other hand, P0 0 is obviously S0 minus S0 0 squared. So we take this expectation further ahead and we have what? 0. This expectation itself is completely 0, and so the conditional variance in the last period is sigma squared, and we are left with P1 0, we are left with phi square. What we are trying to prove here is that the conditional variance, now given enough information, P1 0 is phi square, P0 0 plus sigma square v, the disturbance term. So what was S10? S10 was phi S0 0 plus residual. S10 was phi S0 0, that was it. And the conditional variance of S1 is P10 equals phi square P0 0 plus variance of the disturbance term sigma square v. S10 equals phi S0 0 and P10 equals phi square P0 0 plus sigma square v. That's all. Up until now, this is what we have derived. We have derived P10 and S10, and we have also talked about the conditional variance, which is a square difference between S1 minus S10, which kind of gives us S1 minus S10 gives us phi S0 minus S0, taking one step backward. The prediction error is phi S0 minus S0 plus the variance, and the conditional variance P10 is phi square P0 0 plus sigma square v. So one more time, just the last time, three things we have derived. S10 equals phi S0, S10 minus S1 minus S10 squared gives you phi S0 minus S0 plus variance Vt, and the conditional variance P10 equals phi square V0 plus sigma square v. Thus, expression for the conditional mean and variance of ST given information at time t minus 1. So we need required S0 0 and P0 0. So we need to have the values of S0 0 and P0 0 to represent conditional mean and conditional variance of the latent factor. Conditional variance is P10, conditional mean is S10. But we must have S0 0 and P0 0 at hand. This highlights that the iterative nature of Kalman filter algorithm, as the values of S0 0 and P0 0 will only be available from the updating phase of previous iteration of the filter. So each time we estimate S0 0 and P0 0 and we use it to update the next iteration, okay, because each time S0 0 and P0 0 is used as initial parameters to estimate S10 and P10. So they are updating, they're used as inputs derived from the initial or earlier algorithms and are inputs in the updating phase. So S10 coming from updating phase of S0 0 and P0 0 is, so that's what it is in a nutshell. Observation. So let's taking observation at time t minus 1 from y equals the state equation, the measurement equation, y equals lambda st plus ut. The conditional expectation of yt based on information at time t minus 1 is, the conditional expectation of yt based on information at time t minus 1, the conditional mean is mean ut. The conditional mean is u10 equals e expected, e naught lambda st plus ut lambda e naught st or lambda st t minus 1. So what I'm saying, that conditional mean is, we just derived conditional variance before. Now conditional mean is mu10 equals lambda s10. Now we have derived S10 before, we are gonna multiply that with the factor loading lambda to get the conditional mean. So lambda mu1 0 equals lambda s1 0. And so taking expectation of ut and st conditional upon t minus 1 is available from prediction phase. So from the earlier prediction phase we have already derived. So using s0 0 from updating phase, in the prediction phase we have derived s1 0. So using s0 0 we have derived s1 0, which was s1 0 equals phi s0 0, and this s1 0 is put into then multiplied with lambda, the latent factor, that gives us mu1 0, the conditional mean. We also use that s1 0 to find conditional variance before, and which was s1 minus s1 0, well, squared gives you phi s0 minus s0 0 plus vt, and the conditional variance itself was p1 0 equals phi square p0 0 plus sigma square v, which is a squared variance of disturbance term v and a square matrix basically. And conditional mean on the other hand is simply s1 0 multiplied to the latent factor. The conditional variance of yt is derived by defining one step ahead prediction error. So the conditional variance, so that previously did we talk about conditional variance? No, I'm sorry, p1 0 was just variance, s1 0 was just mean. Now we are the observations we are measuring, where the estimation gives us well, conditional mean, which is lambda s1 0. Now we're gonna talk about conditional variance, which is yt minus that mean, conditional mean we have just estimated, equals lambda st minus 1 plus ut. Basically this equation, or on the other hand, let's express it like that, yt minus y1 minus mu1 0 equals lambda s1 lambda st plus the residual, right, minus lambda st minus lambda s1 0 plus ut. So lambda s1 minus s1 0 plus ut. So the prediction, one step ahead prediction error is now, again, one step ahead prediction error is now lambda s1 minus s1 0 plus ut. Okay, we know that prediction error, one step ahead prediction error is s1 minus s1 0, s1 minus s1 0, the variance is s1 minus s1 0 squared. So obviously the prediction error is s1 minus s1 0 multiplied with lambda plus the residual now. So that so the variance is conditional variance is yt minus the mean u1 0. And what was u1 0? u1 0 is simply s1 0 multiplied to lambda. So yt minus u1 0 squared is now s1 minus s1 0 plus ut whole squared, and s1 minus s1 0 lambda plus ut whole squared, because ut was s1 0 and yt is lambda s1 0 and yt is lambda st, as we know, and in both have ut squared. So then we end up with lambda square p1 0 plus sigma square residual. So vt minus 1, which is v1 0, is lambda square p1 0 plus sigma square. So the conditional mean is s1 0, conditional mean is lambda s1 0, and conditional variance is lambda square p1 0 plus sigma square. The regular variance is the regular variance was phi square p1 0, phi square p1 0 plus sigma square, and the regular and the conditional variance is lambda square p10 plus sigma square. So let's start from the beginning. What did we learn? S10 is phi, S0 is S0, S10 is phi S0 0, then S10 minus S0 0 whole square, or the variance gives you phi S0 S0 minus S0 0, S1 minus S1 0 whole square gives you phi S0 minus S0 0 plus u ut vt, right? Phi. So S1 minus S1 0 gives you phi S0 minus S0 0 vt, and the variance is that was prediction error beginning. Then the variance is p10, which gives you phi square p00 plus sigma square v. Okay, and then conditional mean using the previous mean that so we have done updating and prediction phase, and then we are observing. Observation phase is now turning on and in the algorithm, and the observation phase is conditional mean, which is u10 equals lambda S10 is simply multiplies to lambda, and the prediction error now is y. Variance on the other hand, prediction error is y minus S10, y minus conditional mean u10, y minus u10 is lambda S1 minus S10 plus the residual u, and the conditional variance is now v10 equals lambda square. So we had p10 before, we estimated earlier p10 is phi square phi square p00 plus vt. So now that we are gonna use here, that becomes v10 equals lambda square. Instead of phi square, you're using lambda square p10 plus sigma square. So we, in conditional mean, we used S10, in conditional variance we used p10. So by assumption, tt minus 1 is available from the prediction phase, and the simplification in the last step is simply, so in the simplification, so we have all the information available to us, and we do a simplification in the last stage. That's all. The conditional forecast of factor S is S1 phi S0 vt. We know that S1 equals phi S0 plus vt, or S1 naught equals phi S0 naught. STT minus 1 equals phi S1 equals phi S0. We know that already based on information at time t minus 1. However, yt is available at time t, and so an improved forecast of ST can be derived using this information. Now S1 equals phi S0 is depending on information that is given at time t minus 1. Now if yt is available, we can improve the forecast of S1. To achieve this, the joint conditional normality of yt and st implied by the normality assumptions on ut, so joint conditional normality of yt and st implied by the normality assumptions on ut and vt implies that the conditional mean of st given yt has a linear function form. Normality assumptions of ut and vt, which is IID, implies that the conditional mean of S1 given yt has a linear functional form, which can be expressed as a regular equation. So jointly yt and st have conditional normality, which actually is given by ut and vt. Why yt and st are normal? Because we know that both ut and vt, residual and the disturbance, is IID with zero mean and sigma square v variances respectively, and this normality is given is lent to yt and st, that the conditional mean of st given yt has a linear functional form. Now the conditional mean of st has a linear functional form that can be expressed as regular regression equation. Because we assume ut and vt are id, they are normal distribution, that implies yt and st are normal conditioned upon ut and vt being normal. So yt and st is linear in function, so we can have a linear regression now. Interesting. The linear regression is s1 minus s10 equals kappa yt minus mu1 0, and this is, I think, delta t at the end. We have kappa, and then I'm gonna just pause here. So what do we have here? S1 minus S10 equals to kappa. Inside we have one step ahead prediction error, which is yt minus mu t minus 1 or mu10 plus zeta t. Now zeta t is a disturbance term. Kappa is parameter to be derived. So we can rewrite this. S is equal to S1 equals S1 1 plus zeta t, where S1 equals S10 plus so we have st equals stt plus zeta t, or simply st equals S1 equals S11 zeta t, and S11 itself represents S1 naught plus kappa yt minus the disturbance term, the one step ahead prediction error. Something we learned, this is the meaning that the conditional expectation of st at time t using all of the information up to and including time t, and so we have a least square regression equation where s1 minus s10 is dependent variable and the prediction error is explanatory variable. So we have dependent variable and we have explanatory variable, and kappa is the unknown parameter theta, and we estimate theta based on dependent variable s1 minus s1 naught, explanatory variable yt minus t minus 1 divided by the prediction error, which is the squared and representing variance. So let's revise. What did we do? We are talking about three phases. Updating first is initialization, where we measure up to updating, then prediction, then observation. So first we have S0 and P0 basically that we use so for updating. S0 and P0 that we use for updating, that is updated from previous recursion. And what do we find from there? First we find the first element, which is the mean S10 equals phi S0 0. Then we have variance P10. Then we have one step ahead prediction error, which is S1 minus S10 equals phi S0 minus S0 0 plus Vt. Then we have variance, which is P10 equals phi square P0 0 plus sigma square V, which is the variance of the disturbance term. Then we use them in both of these in our updating in our prediction phase. This phase was updating, I guess. No. We used prediction, then observation, then update. So this information we use to make prediction on S10 and P10, and then we estimate the observations, which are mu1 0, mu1 0 equals lambda s1 0, simply the latent factor. Let's go back to what we were talking before. So we used the prediction information to measure our observation, which is conditional mean, and then the conditional variance is now v1 0 equals, this time the latent factor is getting squared, lambda square p10. P10 is something that we are using from the updating the prediction phase. So p10 plus sigma square. Okay, very simple. So you have observation, mean and variance. Then we move forward, we use these observations into the next stage, which is updating. And now in updating, before we start talking about updating, something we need to understand is that because u and v both residuals are normal, that makes y and s, I mean in the measurement and state equation, to be normal. And if they are normal, using the conditional mean and variance, it is possible for us to derive a regression equation, or I mean s can we can give s a linear function using the information, which actually leads to an improved forecast or improved prediction of s. So because s1 0 equals phi s0 0, we have already an information on that. We can actually, and given the normality we can of s, we can basically improve upon this prediction and come up with a better prediction. And so when y and s is linear in function, we can have a linear regression. And we can solve for the linear regression and have a much better prediction. We can improve upon our prediction. Interestingly, the prediction improves now. The prediction, which was s1 minus s1 0, or the prediction error, which was s1 minus s1 0 equals phi s0 minus s0 0 plus vt, now becomes lambda, insert the bracket, y1 minus mu1 0 plus zeta t. And here y1 minus mu1 0, as we know mu1 0 is conditional mean, y1 minus mu1 0 gives you prediction error. So initially we had phi s0 minus s0 0 plus vt, which becomes lambda y1 minus mu1 0 plus zeta t, and instead of phi we have kappa. Okay, we multiply the prediction error with kappa. Now kappa is a stronger parameter in measuring the prediction error between s1 minus s1 0, and we have a much updated prediction equation based on the for assumed linearity of y and s, and we can simply solve kappa if we consider s1 minus s1 0 on the left hand side to be capital Y, and on the other hand kappa y1 minus mu1 0 to be capital X, which is independent and dependent variables. We can simply solve that for the regular solve kappa or find the parameter kappa simply with regular estimation technique, which is simply yx divided by sigma square, or s1 minus s1 0, in this case s1 minus s1 0 multiplied to y1 minus mu1 0 divided by variance y1 minus mu1 0 squared. As we know, variance is represented by y1 minus mu1 0 because v1 0 was okay. So y1 minus v10 squared, you remember y minus y1 multiplied to x minus x1 divided by x minus x1 whole squared. So that is the only equation. Simple. Okay, so we had predicted parameter that we used for updating, we measured observation, then we improved on the regression equation. So we can further simplify the numerator in this equation, which is y1 minus y10 multiplied to s1 minus s10, sorry, s1 minus s10 multiplied to y1 minus mu10, and we can have lambda p10, and p10 is our variance. So lambda p10 on the numerator, we have lambda p10. So we already have p10 measured, we just simply multiply that with lambda for our numerator, and kappa becomes what? Lambda p10 divided by v10. So you have lambda p10, you have the variance multiplied to lambda, and that is divided with the conditional variance v10. That's it. And throughout all this process, we have already measured p1 and everything. Okay, so in the very first is updating phase, we predicted s1 and p1, and now we know that